So let's take a look at inverse trig functions. All right, I'm starting on page 371. You know that for a function to have an inverse, it has to be 1-to-1. It has to either be always increasing or always decreasing. And trig functions aren't like that, okay? So what we do to make them inversible, I don't know if that's a word or not, but to make them inversible, we have to restrict the domain to find a place where the function is either always increasing or always decreasing. So for instance, for the sine function, if you start at negative pi over 2 and go to pi over 2, the function's always increasing for that. If you go any further to the right, it starts decreasing. It's no longer 1-to-1. If you went any further to the left, it starts, or well, it comes from being decreasing. It's no longer 1-to-1, so it won't work. So the domains have to be restricted, which means that, remember how the domain of a function was the range of its inverse, which means the range of the inverse is restricted, and it ends up all looking like this. That's on page 371. Quite often, our book and other books will use arc sine, arc cosine instead of inverse sine, inverse cosine. Those notations are interchangeable. Be able to read both and use both. Okay? For the most part, if the problem says arc sine instead of inverse sine, then we'll call it arc sine. If they call it inverse sine, we'll call it inverse sine. Okay? Now, don't bother memorizing that. Just be aware that if all of a sudden you're not getting answers that match up with the book, you're probably not operating within the correct domain. Okay? And so then go back and check on page 371 to make sure you're in the right place. All right? Here's what the graphs of the inverse trig functions look like. Remember that graphs of inverse functions are reflections of each other, where the line of reflection is the line y equals x. And remember that the domain of the regular trig function is restricted, and then that domain becomes the range of the inverse function, and you get little odds and ends and little pieces. I mean, that looks okay, that looks okay. These look kind of weird. Well, in fact, the first two do too, when you realize that they just kind of stop. They have endpoints. But again, don't memorize that. If all of a sudden you're not getting the right answers anymore, look back on page 372 and go, oh yeah, the arc cosine function doesn't go from negative infinity to infinity. That's what's leading me astray. Okay? Some things that you need to remember. All right? Inverse functions. F of f inverse of x equals x, f inverse of f of x equals x. That's always true. It's always, always, always true. Now, for these inverse trig functions, the arc secant of x is the same thing as the arc cosine of 1 over x. Now, why would we want to do that? Well, because on your calculator, you won't find an inverse secant button, will you? Will you find an inverse cosine button? Yep. So, when we're down to having to use calculator or a trig chart or a unit circle, we'd really rather have cosine than secant. We'd really rather have sine than cosecant. So the arc cosecant of x is the same thing as the arc sine of 1 over x, and we'd really rather have tangent than cotangent. So the arc cotangent of x is the same thing as the arc tangent of 1 over x. Also remember these three things, that the sine of negative theta is the same thing as the negative sine of theta. Tangent works the same way. Cosine doesn't. The cosine of negative theta is the same thing as the cosine of positive theta. So those last three especially are things you should have already been familiar with, but you need to have them back in your short-term memory, okay? All right. On page 374, In section 5.1, you saw that the derivative of the transcendental function just means non-algebraic. F of x equals a natural log of x is the algebraic function f prime of x equals 1 over x. So a non-algebraic function had a derivative that's algebraic. You will now see that the derivatives of the inverse trig functions are also algebraic, even though the inverse trig functions themselves are not. So this theorem gives us the derivative of the 6 inverse trigonometric functions. Note that the derivatives of arc cosine, arc cotangent, and arc cosecant are the negatives of the derivatives of arc sine, arc tangent, and arc secant. So it works this way. There's the derivative of inverse sine of u, arc sine of u. The derivative of inverse cosine, arc cosine, is the exact same thing with a negative in front. The derivative of arc tangent and arc cotangent are the exact same thing, but arc cotangent has a negative in front. The derivative of arc secant and arc cosecant are the exact same horrible looking, ugly thing, with the exception that arc cosecant has a negative in front. Okay? Now, you do need to memorize those. And they're horrible looking, aren't they? So, have fun with that. Make a game out of it. Flashcards. All right. Now, we've got a lot of derivatives. Okay? So, just a little history here. In the 1600s, Europe was ushered into the scientific age by such great thinkers as blah, 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 blah. Oh, there's one I care about. These men believed that nature is governed by basic laws, laws that can, for the most part, be written in terms of mathematical equations. Even if some of them weren't exactly right, they did a pretty good job of describing the things that happen in the world. One of the most influential publications of this period by Galileo has become a classic description of modern scientific thought. Be sure to ask your English teacher to assign that for a little light reading to the rest of the class. As mathematics has developed during the past few hundred years, a small number of elementary functions has proven sufficient for modeling most phenomena in physics, chemistry, biology, engineering, blah, blah, blah. I like the fact they call these elementary functions. Everything you've ever done in math, mathematicians consider that to be elementary. And they do tell us that some important functions used in engineering and science are not elementary. I don't even want to see those. Okay? So an elementary function is a function from the following list, or one that can be formed by making the sum, product, quotient, or composition of one of the elementary functions. So let's see how many we actually think we know. Algebraic functions, polynomial functions. Yeah, we're good, right? We can take their derivative, we can take their integral, we can do anything we want with those. Rational functions, a little tougher because now you've got a denominator, but the quotient rule helps us out. Making substitutions makes it easier to find integrals. We can do that. Radicals, especially if we rewrite those radicals as exponentials, we can take derivatives with the chain rule. We can use substitutions to get integrals. We can do those. Logarithmic functions, yeah, we've learned how to take the derivative and integral of those. Same thing with exponential. Trig, we kind of been working on all year long, taking derivatives and integrals. So that's where we are now. Okay? So since we're coming up with these new ones, the book decided this would be a good time to show you this. That's what you're supposed to be able to take the derivative of so far. Probably. It's on page 376 this time, and it's in your book in various forms several times where we'll add things onto them. So, know those. Know them all. Now let's do some. Let's work with our inverse trig functions a little bit. So number 8 on page 377 says to evaluate the expression without using a calculator. So we have the arc cosine of 0. Well, if you've got your unit circle memorized, or you've got your trig table with you, the arc cosine of 0 is the angle whose cosine equals 0. So either have it memorized or look it up. What angle has a cosine that's equal to 0? Pi over 2. And we do want it in radian. 45 degrees is correct, but we want it in radian. So pi over 2. 90 degrees, like I said. Who said 45? I didn't say 45. You can't find it on the recording where I said 45. 90 degrees. Sorry about that. Wow, that's like the 12th mistake so far today. They're adding up. What's your domain? All right, now we're going to evaluate some more complicated things. Number 10, we have the arc cotangent of negative square root of 3. I don't like arc cotangent. I'm going to change it to arc tangent. So I've got to make it the arc tangent of 1 over, forgot the negative, negative 1 over the square root of 3, don't I? And then that's the same thing, because I'm not going to be able to look that up on a unit circle or a table. I'm not. Because they're going to write it in simplest radical form. So that's the same thing as the arc tangent of negative square root of 3 over 3. Now, the tangent of negative theta is the same thing as the negative tangent of theta. So that'll be negative whatever the arc tangent of radical 3 over 3 is. And that's pi over 6. And then if you look in the book, they might also say 5 pi over 6. And that's one of those things where if I made you memorize the domains and the ranges, you would know whether or not to look for another. And I'm not real worried about that right now. Okay? So be able to come up with an answer, and then when we're doing an application, we'll worry about whether or not we've got one that's in the proper domain. Okay? So negative pi over 6 or 5 pi over 6. Number 18. Here we need to evaluate each expression without using a calculator again. All right, now, you probably don't know why yet, but I've written out the Pythagorean theorem here. And it's easy to solve for C, right? I probably should have written that out here. C would equal the square root of a squared plus b squared. But I've got it solved for a and for b. The thing you need to remember, you don't have to memorize that. But if you're solving this for one of the legs, it's square root of, and then the hypotenuse squared minus the other leg squared. So a would be the square root of hypotenuse squared minus the other leg squared. Okay? Now, here's why. For 18, let's find the tangent of the arc cosine of square root of 2 over 2. So we have a composite function where one of our functions is an inverse trig function. So, a little bit complicated. What we're going to do to solve this is we're going to go back to right triangle trigonometry. I'm going to let the arc cosine of square root of 2 over 2 equal theta. I probably should have written it the other way around, because we've always written let u equal whatever. So let theta equal, then what do we let u equal a lot of times? A quantity inside of parentheses, right? So let theta be the quantity that's inside the parentheses, the arc cosine of the square root of 2 over 2. Now, before I show you what I have written next to my paper, let's figure this out together. If I go back to right triangle trigonometry, and I put theta right there. The arc cosine of square root of 2 over 2 is theta, right, equals theta. So doesn't that mean that the cosine of theta equals square root of 2 over 2? And cosine is adjacent over hypotenuse. So the adjacent leg has a length of square root of 2. The hypotenuse has a length of 2. You with me? You see how that became that? Now, I need to solve for that missing egg. Because if I do, then I can answer I can write any trig ratio because I've got the triangle to look at. You can follow my logic? All right, so it would be the square root of the hypotenuse squared minus the other leg squared. So the square root of the hypotenuse squared minus the other leg squared. So that's the square root of 2. So that's what I had written there. So I need you to follow the logic. Turn what's inside your parentheses into theta. Use theta to make a right triangle. Once you have the right triangle, you can write any trig ratio that you're asked to write. Which one are we asked to write? Tangent. So since what's in the parentheses is now theta, all we got to do is write the tangent of theta. Tangent's opposite over adjacent. Square root of 2 over square root of 2, 1. So the tangent of the arc cosine of the square root of 2 over 2 equals 1. It is kind of weird. Huh. I don't think you got that memorized right. For B, we've got the cosine of the arc sine of 5/13. What are we going to let theta equal? Arc sine of 5/13. When you draw your triangle, sine is opposite over hypotenuse. So put theta as one of your acute angles. Does it really matter which one? No. All right, so then the sine of theta will be 5 over 13. And then solve for that missing one. So the missing leg is the square root of the hypotenuse squared minus the other leg squared. So that's the square root of 169 minus 25. That's the square root of 144. That's 12. Now we can write any trig ratio that we want. We want cosine. Some of you are looking a little confused. Maybe I need to do this. If the arc sine of 5/13 equals theta, by definition of inverse trig functions that you learned from me in geometry a few years ago, that means that the sine of theta equals 5/13. We actually did it this way. We learned this and said that that means the inverse sine of 5/13 equals theta. Okay? Does that help? Okay.